We present LiSTA, LiDAR Spatio-Temporal Analysis for geometric object-based change detection in cluttered environments. Many applications require such a system for object-level change detection, including robotic navigation, long-term autonomy, and environmental monitoring. We focus on the semi-static scenario where objects are added, subtracted, or changed in position over weeks or months. Shown here is one of the experiments performed mapping the Fire Service College using a Boston Dynamics spot with our in-house sensor suite mounted. So our system is a LiDAR Spatio-Temporal Analysis tool for object-level change detection. The contributions are as follows. Our system consists of 5 steps, the first being multi-mission LiDAR SLAM, allowing for robust registration between missions over time. Then we perform volumetric reconstruction and differencing. We can then segment change objects and perform open set object instance description with a neural network. We can then cluster the object descriptors to determine classification of objects giving labelless classes. And finally, we estimate the exact correspondences between missions. The SLAM mission data is acquired using our in-house sensor suite, the Frontier, shown here mounted on a Boston Dynamics spot. The system uses our LiDAR inertial odometry system, LiDAR SLAM, as a basis for pose graph optimization. To register maps from different missions in a common reference frame, we perform multi-mission pose graph SLAM, performing both intra-mission and inter-mission loop closures. We can get a 4D map representing the entire environment explored by the robot across time. These maps were acquired by the Spot robot, where the first mission was executed with teleoperation and subsequent missions were autonomous, following the same pose trajectories. To get quantitative evaluation metrics, we ran our system on simulated LiDAR data. The simulated data consists of 3 offer scenes, each with 2 missions for object level change. Once the difference cloud is determined, we can segment the discrete objects to get point cloud clusters. We then generate a 3D feature descriptor using an adapted neural network Instalog, and we can classify these descriptors into labelless classes. Within these classes, we find object correspondence estimates by minimizing the weighted descriptor and physical distances of the objects. Once we have the exact correspondence, we can determine the transformation between alike objects using singular value decomposition. One of the experiments is shown here. The identified changes are shown here in blue and the static cloud shown in red. And here each classified object is shown in a discrete color according to its class, and correspondences shown with black lines. We put LiSTA to the test with a real-world experiment too at the Fire Service College, the results of which are shown here, where the static map is shown in blue and changed objects are shown in red. Thank you for listening.